Okay, now we are interested to know how to generalize this problem as well as our estimation. This is a dimension 2 case. How about generalizing this problem to the dimension n case? In the dimension n, instead of having a circle or a disk, we're going to have a ball of radius r. And in that case, we would like to count the number of integer points inside that ball. So those notations has to be changed. First, let's put a subscript n to denote the dimension of our problem. And this time, we are going to have an integer valued vector in the dimension n case with n components. So we'll have k sub 1, k sub 2, all the way to k sub n belonging to Zn, where the sum of squares is less than r squared. And same for the n theta case, except that instead of less than, we'll put less than or equal to allow those integer points to lie on the boundary of our ball, namely the sphere. Now we'll be interested to estimate the difference between n sub n or n sub n tilde of r and this time the volume of this ball. Let's use the notation v sub n of r. Recall that by the multivariable calculus, this n-dimensional ball volume will be equal to 2 pi raised to the power n divided by 2 divided by n times gamma of n divided by 2. So this is the gamma function. And the factor that is related to r will be r raised to the power n. This is the formula for the n-dimensional ball. Our idea for this estimation will be the same, except that we will change the words areas to volume. And now we'll see what the estimation looks exactly in our proof. The picture will be the same, except that you should imagine there's something in higher dimensions. And we are taking the collection of cubes. Now this stands for cubes. And let's change the notation from S to script C. The script C stands for the cubes. So here we are going to change this to the volume, the nth volume of the ball with radius r. And we are going to change this S to C. Oh, I forgot. So this Z2 will be replaced by Zn. So we are going to consider the cubes in script C in two cases. The first, those cubes that are contained in the ball centered at the origin with radius r, or those cubes which has non-empty intersection with the closed ball centered at 0 with radius r. the first one, we still keep the first one to be the open ball in order to get the maximum possible difference. And we also need to change this to the volume. So this will be BNR, so BNR. And now, because each cube is still a cube of set length 1, which means each cube has volume precisely equal to 1. So those numbers will equal to the volume of the union of those cubes, respectively. So this area will become the volume. And now, when we do this majorization, when we consider two balls, one of them has radius bigger than this given ball of radius r, and another is smaller. What do you think the radii of those new balls will look like? I will let you think about it. Previously, we have the bigger ball with radius r plus square root of 2. So previously, this distance is square root of 2. And for the smaller ball, we have the radius equal to r minus square root of 2. So this distance is also square root of 2. Now, in the nth dimension, do you expect that square root of 2 to be something else? Yes, of course. Because previously, the root of 2 corresponds to the length of the diagonal of your unit square. Now, for the unit cube, the diagonal will have the length square root of n. So this will become the volume of the ball with radius r plus square root of n, and this is the volume of the ball r minus square root of n as a radius. And again, this argument will be valid only for the case when r is greater than square root of n. And remember, by our formula for the volume of dimension n balls, this guy will be equal to this thing, and the second guy will be equal to this. What is really important is this part. We do not care too much about the coefficients, because the coefficients are the same constant that only depends on n, and here n is fixed. And we only care about the subtraction of those two things. When you take the subtraction, you know the term with the highest power will cancel out. So the Rn is going to cancel out with Rn in here. And in the end, we'll get something that is the big omega of r raised to the power n minus 1, which is the dominating term in here. So in the end, the error we are going to get will be nr theta with subscript n here, minus the volume of ball with radius r in dimension n equal to the big omega of r raised to power n minus 1. Although our argument is only valid for r greater than square root of n case, however, when we consider this error, we mainly only concerned about the case when r is big, because here n is fixed. When r is big, we're going to get this. Actually, what's going on when r is less than or equal to square root of n will be a complete different story. So what happens when r is less than or equal to square root of n? In that case, this inner ball will collapse to nothing. But you still have this guy bounded above by this first term. That will be a very generous bound for this, for the r, for the case when r is less than or equal to the square root of n. So this guy will be bounded by the volume of n-dimensional ball of radius r plus square root of n. And this is less than or equal to the volume of the ball with the radius 2 times square root of n when r is less than or equal to root of n. And this in turn is bounded by this constant. So now the radius is 2 times root of n raised to the power n. But anyway, you know this is a constant that only depends on n. So when r is less than or equal to root of n, this is bounded by a constant that depends on n. So if r is greater or equal to 1, but less than or equal to square root of n, this absolute value and tilde of r minus bnr, which is bounded by c sub n, be still less than or equal to c sub n times r raised to the power n minus 1, because r is greater or equal to 1. So in this range, this guy is still a big omega of r raised to the power n minus 1. And if r is less than 1, then you know this guy has a precise form. So this n tilde now will just consist of 1 point. So this number will just be 1. So the n tilde r, when r is less than 1, will just be equal to 1. And the second guy will be this constant multiple of r raised to the power n. When r is very, very small, close to 0, this could be way bigger than r raised to the power n minus 1. Because in that case, r will go to 0. But this case is not interesting because it is too trivial. So anyway, we proved that for r greater or equal to 1, we have this arrow is equal to the big omega of r raised to the power n minus 1. And you know how to translate this argument to the case where this n tilde is replaced by n. The argument will be very, very similar, except that in here, Maybe you want to replace this by the open ball. You can also choose not to change that, and you will get the same answer. So this finishes our discussion in higher dimensions.